There are many reasons to learn about XAML's shapes, paths, and geometries. You might want to create customized art as part of an application, or create custom controls where you have to generate the UI yourself. Maybe you want to add interactivity to graphics, or use animation where you animate a shape. Or perhaps you just want to create any non-standard user interface. To make this work, you'll start by looking at simple XAML shapes. These are classes that inherit from the system.windows.shapes.shape class. And then we'll move on to examine geometries and paths, which are more full-featured, but of course more effort as well. Now we'll start by investigating basic shapes. More complex means do exist, but the simplest solution is to use built-in classes that represent lines, ellipses, rectangles, and polygons. That is, before you go any farther, try to use these. These exist as elements, just like text block, canvas, and all the other elements that make up your XAML markup. There are some built-in benefits from using these shapes. For example, shapes take care of their own drawing. You don't have to do anything, just put it in your markup and it works. Shapes can be contained like other elements. They are other elements, so you can put a shape inside a canvas or a grid cell or any other container. And shapes handle events like other elements, so you can handle, well, a click event, for example, of a shape. All basic shapes inherit from the system.windows.shapes.shape class, so they share some common behaviors. That's an abstract class. You can't actually create an instance of that class. Instead, you'll use classes like rectangle, ellipse, line, polyline, polygon, and path, and we'll look at all of these in this section. The shape class, that is the base abstract class, provides its own set of useful properties. Things like fill, that's what goes inside the shape, stroke, that's what defines the border of the shape, and stroke thickness, well, that's the thickness of the border. There's a stretch property that defines how the shape gets stretched. There's stroke start line cap and stroke end line cap, and these control the contours of the beginning and the ending of a line. They don't really have any effect on closed shapes like a rectangle, which don't have a starting and ending point. Stroke dash array, stroke dash offset, and stroke dash cap all control the border. You can add a dashed border around a shape, or a line can be dashed. These properties allow you to control the size of the dashes and the spaces between them, as well as the contour of the leading and trailing edge of each dash. And we'll look at this in probably far too much detail in just a bit. There's the stroke line join and stroke miter limit properties, and these determine the behavior of the corners of a shape. And these have no effect on shapes that don't have corners like lines and ellipses. The stroke line join property specifies a pen line join value. The options are miter, bevel, or round. And stroke miter limit gets or sets a value on the ratio of the miter length to the stroke thickness of a shape. So you can control how much of a corner you get on a shape that has a corner. Let's start with the simplest shapes, that is, rectangle and ellipse. You can supply any or all of these properties: the height and width, the stroke, that's the border, and the fill. You can specify a min height and min width property. You can specify a margin. Also, horizontal alignment and vertical alignment apply to these shapes. Now, before we look at these shapes, let me talk a bit about rounding corners on a rectangle. The rectangle class adds to the properties provided by the shape class radius x and radius y properties. These control the rounding of the rectangle's corners. Basically, these properties define an ellipse that describes the rounding of the corners. The radius x property provides half the width of the ellipse, and the radius y property provides half the height of the ellipse. You have to imagine an ellipse in your mind, and radius x is from the center to the horizontal edge of the ellipse, and radius y goes from the center to the top or the bottom of the ellipse. The minimum value is 0, and the maximum value is half the width or the height, depending on which one you're setting, of the shape. As you'll see, if you round a rectangle with values larger than that, you just end up with an ellipse. Let's look at the demonstration that shows how you can create shapes and how you can round the corners of a rectangle shape. I've run the sample project, Shapes and Geometries, and you can see it's just a tab control where each tab contains a single user control that demonstrates one feature I'd like to show off. In this first user control, we have 3 shapes: a rectangle, an ellipse, and another ellipse. You can see that the fill color is different on the 3 shapes, and each has a stroke, a border that's black, that's about 2 pixels wide. Let's look at the markup for this user control to see how it's doing its work. You can see here that I have a stack panel, and within that stack panel I have our 3 shapes: a rectangle, then an ellipse, then another ellipse. The rectangle has its fill set to yellow. It's a solid color brush, and we could use a different kind of brush, and we'll cover using brushes in a different part of the course. You can see the height is set to 100, and the width is set to 200. The margin is 5, so we have space between the shapes, and we have a black stroke property and a stroke thickness property of 2. For the ellipse, we have all the same properties, except the fill is a different value. It's red instead of yellow. But otherwise, all the properties are the same. As a matter of fact, all I did was copy and paste, change the element type, and change the fill, and I got a different shape. For the final shape, the only differences are the fill color, which is blue, and the width, which is 100. So we get a circular shape rather than an oblong elliptical shape. Well, those are simple, and it shows how you can use the shape elements, set a few properties, and you end up with a shape within your container. Let's look at rounded corners. Here I have 4 rectangular shapes. Yes, the bottom one is a rectangle with radius x and radius y values set. You can imagine here, for example, that I have an ellipse where half of its width in the x direction is 10 and half of its height in the y direction is 10. So we end up with a circle here whose upper right quadrant defines the rounded corner here. We have a circle down here whose lower right quadrant defines the rounded corner here, and so on. In our next example, we have the same rectangle, but this time we have an ellipse whose width is 100 and whose height is 20, sitting here in each of the corners, defining the rounded edge. Here again, we have a height of 50 and a radius y of 50, so we get the shape you see here, where an ellipse defines the entire side. It looks like we have an ellipse that made up this side. And finally, here we have, well, this is weird. Look at that. We have a width of 200, but a radius x of 100, meaning the ellipse itself that defines the corners has a width of 200. Same for the height. Well, this is the exceptional case. That is, you've defined an ellipse that defines the roundness of the corners that is the same size as the rectangle itself, so you end up with just an ellipse. Don't do this. If you're going to use rounded corners, you want something like these first few options, which define gradually rounded corners, where an ellipse defines the shape of those corners. The markup for these is very simple. It looks exactly like what you see here, except we also have colors and stroke and all that sort of thing. Those don't matter in this example. All we care about is the radius x and radius y property that defines the roundness of the corners of the rectangle. Although you can specify the size for a shape, as you saw in the previous demonstration, you may find it useful to allow the shape to fill its parent container. That way, you can size the shape dynamically based on its parent container. To make that happen, you use the stretch property of the shape to control its behavior. The fill value, which is the default, causes the shape to stretch in both directions to exactly fit the parent container. And if you set the width and height properties explicitly, this doesn't really do anything. there's none, and in this case the shape doesn't stretch, and you must explicitly provide either width and height and or min width and min height properties in order for the shape to appear at all. Listen carefully. If you set the stretch property to none, you must specify the size of your shape or it simply won't appear at all. Uniform uses the smaller of the width and height. Basically, the shape expands until it reaches the edge of the container. For a rectangle, this setting provides the largest possible square that fits within the parent. For an ellipse, it provides the largest possible circle that could fit completely within the parent shape. Uniform to fill uses the larger of the width and the height. In this case, the shape stretches in both directions proportionally until the shape reaches the edge of the container, and the shape may be truncated because it doesn't all fit, because you're using the larger of the width or the height. For a rectangle, this shape provides the largest possible square that fits within the parent, and for an ellipse, it provides the largest possible circle with possible truncation. Let's look at an example that demonstrates the behavior of these options. In this example, we have 3 grid cells containing the same ellipse. If I look at the markup, you'll see that the ellipse is set in each case without setting the size explicitly, but you can see the stretch is set to fill, the stretch is set to uniform, or the stretch is set to uniform to fill. In each case, the color is different, but that's the only difference. And you can see with an ellipse set to fill, it stretches its width and height till it fills the entire parent cell. I've turned on Show Grid Lines so you can see where the cell grid lines are. I also have a margin set, so there's a little space around the shape. In the next example, the red one, we have the stretch property set to uniform. And in this case, the shape does fill the smaller of the 2 dimensions, so we end up with the largest circle that can fit completely within the cell. Finally, in the last example, we have uniform to fill set for the stretch property, and in this case, the ellipse provides the largest circle that can fit within the parent with some possible truncation. In this case, we're using the larger of the width and the height, and of course that causes our circle to be truncated. I haven't demonstrated the none option because that's basically what we were using in previous examples. And in those cases, we had to specify the width and height to indicate how large we wanted the shape to appear within its container. But if you set stretch to fill, or uniform to fill, you get the behaviors shown in this example. Had we used a rectangle, it would have been exactly the same, except we would have ended up with a small square in the middle and a large square on the right. You can use any standard containers when you want to place a shape onto your application. Canvas makes the most appropriate choice when working with shapes because you can explicitly position each shape within the canvas. To do that, you use the canvas.left and canvas.top attached properties, so you can specify exactly where your shape appears. Now, it's important to understand that the order of the markup is significant too. That is, the order in which you place the shapes within the markup. Each subsequent element appears on a higher layer within the rendering, so that if you have a rectangle first, then an ellipse, the ellipse will appear above the rectangle if they happen to overlap. Now you can use the canvas.z-index attached property to control that layer placement. That is, if you have a rectangle and then an ellipse, you would normally see the ellipse on top of the rectangle. But if you have the rectangle's canvas.z-index property set to a higher number, it will appear on top. What if 2 shapes have the same canvas.z-index property? Then the ordering within the markup controls their placement in terms of what appears on top of the other. This can get complicated, so you have to keep both those values in mind when rendering the shapes. Order within the markup controls what appears on top unless you override that with canvas.z-index, and if 2 items have the same canvas.z-index value, then it's the ordering that controls what appears on top of what. I have an example that demonstrates some of these issues. On the positioning shapes example, we have 3 different shapes displayed 4 different times. In the first one, the natural order is being used for displaying them. And in the markup, we have the yellow rectangle, then the red ellipse, then the blue rectangle, and since we haven't specified canvas.zindex for any of these, they appear in that order: yellow rectangle, red ellipse, then blue rectangle. Now in the second example, I've changed the order. In this example, and for the rest of these examples, the blue rectangle comes first, then the red ellipse, then the yellow rectangle. That's the natural order: blue rectangle, red ellipse, yellow rectangle. In the next example, I modified it by changing one thing only. I changed for the blue rectangle, I set the canvas.zindex property to 1. So in this case, in this example, the blue rectangle pops to the top. Otherwise, here, the yellow rectangle and the red ellipse share the same canvas.zindex value. I didn't specify it, so it's 0. So the natural order of the elements controls the ordering in layers in the output. In the final example, the natural order is the same: blue rectangle, red ellipse, yellow rectangle. But in this case, I set the canvas.zindex property for the ellipse to be 1 and for the blue rectangle to be 2. So the blue rectangle pops to the top, the ellipse is in the middle, and the yellow rectangle is on the bottom. Remember, the natural order, if you look at the markup, is blue rectangle, red ellipse, yellow rectangle. So yellow rectangle should be on the top, but it's not because I set the canvas.zindex property for the ellipse to be 1, which moves it up a layer, and for the blue rectangle to be 2, so it moves it up yet another layer. Those canvas.zindex values, they're just relative numbers. Pick any number you want. It's the relative values that control the layering within the output here. If you want to resize shapes once they're placed in your design, the easiest way to do that is by using a viewbox control. You can embed your canvas within a viewbox and then set the stretch and stretch direction properties to control the behavior of your shape. You've already seen the stretch property. The stretch direction property can be one of up only, which means your shapes will only enlarge. They'll never get smaller than their design time coordinates. There's down only, which means things only shrink. They never get larger than they were at design time. Or both. Things shrink and grow. That's the point of the viewbox, is to make things inside it change shape. When you use a viewbox control, the default value for stretch is uniform, and that means the viewbox only stretches its contents to the minimum of its width or its height. You can use the stretch direction to control how stretching or shrinking works. Now, it's important. The viewbox control needs both the original size and the new size in order to be able to stretch something. If the container doesn't supply its size, if it itself gets the size from its parent, then the viewbox can't resize it. So it's important that if you want to use the viewbox, the container that you're using for your shapes has to specify its original size, so the viewbox can resize it. Sometimes you set a canvas up just to have no coordinates so it fills its parent container. In that case, the viewbox isn't going to help you because you won't be able to resize things. In our example, the canvas control specifies its size so the viewbox can resize it. Let's look at some examples that demonstrate using the viewbox control. In this example, I have the same set of 3 shapes, they should look familiar by now, placed into 4 differently sized grid cells. In each case, we have a canvas control placed within a viewbox, and the viewbox fills the parent cell. Let's look at the layout for this. You can see that we have columns defined where one is twice as wide as the other, and we have rows where one row is twice as tall as the other. And down here we have a view box in the upper left-hand row and column. And you can see we have a canvas whose width and height is 300 and 200. Remember, you have to set the width and the height, or you can't resize this using the view box. And inside that canvas we have our rectangle, ellipse, and rectangle that you've become so familiar with already. Then we have another view box in grid.row1 and grid.column 0, so that's in the bottom left-hand cell. And the only difference on this one is nothing. It's exactly the same. As a matter of fact, all I did was copy and paste the markup for the view box 4 times, well, the original, and copy and paste 3 times, modifying the row and the column. Otherwise, the markup is exactly the same for each one of these 4 view box controls. The only difference is the row and the column, and you can see just by doing that, we have a differently sized and shaped set of shapes in each one of those cells. So the view box takes care of that for you. The only trick is you have to specify the size, the original size, for the container for those shapes, or you won't be able to resize them using the view box control. The next shape we'll look at is the line shape. As you might expect, the line shape represents a straight line that connects 2 points. You define the points, the shape draws the line. You must set 4 properties to describe your line: x1, y1, x2, and y2. And as you'll see later, the fact that you have to set 4 properties here makes this shape a little arduous to have to set up very much. There's other ways to do this, but if you're only drawing one line, sure, this is the simplest way to do it. Only provide straight lines. There's no fill property because it's just a line. You have to supply the stroke property to define what color or what brush you want to use to draw this line. And the coordinates are relative to the upper left-hand corner of the container of the line. If you're placing the line into a cell, then the coordinates are relative to the upper left-hand corner of that cell. If you're placing the line into a stack panel, well, you got it. The coordinates are relative to the upper left-hand corner of that stack panel. Negative coordinates are okay. You may find it useful to start the line outside the container it's sitting in. And you'll notice that there are some attached properties from the parent. For example, if you place the line into a canvas control, the canvas.left and canvas.top properties still apply. And then you add those to the x1, y1, x2, and y2 properties. In other words, if you set the canvas.left and canvas.top properties of a line shape, then the coordinates of the line are in addition to those settings. They respect those settings. Let's look at an example that demonstrates how you can create line shapes. In this example, we have 4 lines, each one contained within a canvas within a grid cell. In the first one, we're using just x and y coordinates to define the behavior of the line. Let's look at it here. You can see that our line goes from 10, 20 to 400, 80. Its stroke is black and its thickness is 4, and we get a plain old line. In the next example, we have, well, not quite a black brush anymore. This time, it's a linear gradient brush that defines the stroke for this. And in that case, you can see the markup looks much the same, except for the stroke property. Up here, stroke was a simple value, black. Down here on the next example, because I want to use a linear gradient brush, I have to use this element.property syntax, because you can't just specify the property value as an attribute. You've seen this behavior before, and here I'm using a linear gradient brush to define that stroke, and although we haven't yet talked about linear gradient brushes in this course, and we will in far too much detail in a different part of the course, for now you've probably seen a linear gradient brush defined already, so I'll assume that you can at least follow the steps there. In our third example, we have negative coordinates. You can see here that the line starts outside of its container. That works fine. If I go to the example markup here, you'll see that I'm just using negative coordinates for the starting point for this line. No problem with that. And our final example not only has its x and y coordinates set, it also has the canvas.top and canvas.left properties set, so that the line is offset 50 pixels from the left and the top before its own coordinates kick in. You can use that canvas.left and canvas.top properties to offset all of the elements within a given canvas, so you can offset everything by a specific amount. In any case, here's 4 different examples of 4 different ways to use a line element, and you can see the different behavior in the example. By adding line caps, you can control how starting and ending edges of lines appear. You set the stroke start line cap and stroke end line cap property, and notice that these properties have no effect on closed shapes like a rectangle, ellipse, or polygon. It only affects things that have ends. That's sort of the point of this exercise. And of course, you can set a line cap at one end or the other. The start line cap always goes on the end of the line defined by the x1, y1 coordinates, and the end line cap, of course, goes on the point, the end of the line defined by x2 and y2. Now you've got some options here. You can add a flat line cap. This is the default, and the line ends immediately at its starting or final value with no extra stuff. You can add a round line cap, and in this case that line ends with extra space, and the importance is how much extra space, and the extra space is half the thickness of the line with a rounded cap. Square adds extra space, half the thickness of the line with a squared off cap, which makes it look just like the line itself with some extra space at the end. And there's a triangle line cap. This adds extra space, half the thickness of the line with a triangular cap. Let's look at an example that demonstrates this. This demonstration shows off all the values for the stroke start line cap and stroke end line cap properties. The default is a flat line cap as shown in the first example. Here we get the length of the line. Here's a 20 pixel wide line. Here's a 10 pixel wide line. With a flat line cap, the line is what it is. In the next example, I set the stroke start and stroke end line cap properties to round, and you can see the line's a little longer because all these lines are defined exactly the same length, but you can see this adds half the thickness of the line to the end of the line. Same thing here, and we get those rounded line caps on both ends. Here we have the square line cap, which looks just the same as the flat line cap, except it adds, how much you ask? Half the width of the line, half the stroke thickness property as a squared off line cap. And finally we have the triangle line cap, which adds half the width of the line as a line cap and a triangular point. So you can use any of these values in the stroke start line cap or stroke end line cap property of the line to change the behavior of the ends of the line. You can also create dashed lines, that is, alternating line fragments and spaces. That's all a dashed line is, and you can use this any place you use a line, including on the stroke of an ellipse or a rectangle. Any place you have a line, you can do this. You can control both the line fragments and the spaces. You specify the length of the solid and the blank portions of the line. And to do that, you set the stroke dash array property to one or more values. Now this requires some study to get completely correct, and for me, I just had to play with it for a while before I got it all worked out in my head. The stroke dash array property allows you to specify values, and the values you specify relate to the value of the stroke thickness. Remember, the thickness is how thick the line is. If you specify a value of 1, that means your dash or space will be the same as the thickness of the line. If you specify 0.5, it's half the thickness, or if you specify 2, it's twice the thickness of the line. You can specify both whole or fractional values. Now, when you specify the values in your stroke dash array property, the first value indicates the size of the solid piece, and then the next value indicates the size of the space piece. If you only specify one value, it applies to both the solid and the space. So if you specify 1, for example, you'll get a solid part, then a space part, then a solid part, then a space part, all whose width is the same as the stroke thickness of the line itself. If you supply an even number of values, they're repeated so that the dashes and the spaces are consistent. Imagine you've specified 2 and then 1. That's the two values you specify. The solid part will be twice as thick as the line thickness. The space will be the same thickness as the line thickness, and then that will just repeat for all of the dashes that make up the space of the line. If you supply an odd number of values, but more than one value, the pattern repeats so that dashes and spaces are inconsistent. That is, imagine you've specified, 2, 1, and 2. We'll look at an example of this later on. 2, 1, 2. 2 is the thickness of the first solid part. 1 is the thickness of the first space part. 2 is the thickness of the next solid part. But now that pattern repeats. The next thing that comes up is the first 2, which now represents the thickness of the next space part. The next 1 represents a solid part, and so on. You have to see it, but I'm trying to get your brain thinking about this. What if you want to start part way through the stroke dash array values? You'll need this if you ever want to animate your dashes. Imagine, as Microsoft Word does, for example, sort of dancing dashes around a border of something. In that case, you might want to specify that at first you start at the first value, then you start at the second value, and maybe you alternate back and forth so your dashes and spaces animate. To do that, you can set the stroke dash offset property. That indicates in units of the stroke thickness how far to start into the array, and it makes it possible to animate the dashes. We'll look at examples of this. You can also add line caps to each dash. Set the stroke dash cap property to do that. Notice that this adds extra width to both sides of the dash, and since the cap adds half the line thickness to each side, you end up adding a full thickness of the line to the dash when you add a dash cap. This means you have to add extra space to make up for it, and to do that you probably want to modify the space portion of your stroke dash array to give you more space to work with. If you set the stroke dash cap property, you should probably set the stroke start or end line cap to match, so the end or the beginning of the line matches all the dashes in the middle. Well, that's a lot to think about. So let's look at a bunch of examples that define some dashes in an example. In this example, with tons of lines on the screen, we're going to look at all the different possible ways you can use the stroke dash array property along with the stroke dash offset and stroke dash caps properties. In the first example, actually in all the examples, we have a 12 pixel stroke thickness for the line. And if I set the stroke dash array property to 2, that means that we're going to use twice the stroke thickness for both the solid part and the space part. So this is 24 pixels wide, this is 24 pixels, this is 24 pixels, that's 24, and so on, in a repeating pattern. In the next example, with the stroke dash array property set to the string 2 space 1, you can use a comma if you want, but you don't need to use it. 2 space 1, here we get 2 stroke thicknesses for the solid part, 1 stroke thickness for the space part. Then that pattern repeats with 2, 1, 2, 1, and so on. Actually, in your brain, you can probably imagine a little grid here which specifies 12 pixel chunks. And you can see we have 2, 1, 2, 1, and so on. The next pattern's a little different. This one specifies an odd number of values in the stroke dash array, but more than 1. So in this case, we get 2, 1, 2, then 2, 1, 2, and the pattern just keeps repeating. 2, 1, 2, and then it changes to have the space be 2, stroke thicknesses wide, and so on. Finally, you can use a partial value of the stroke thickness. Here I've specified 1 and 0.5, so this is 1 stroke thickness wide. It's a little square, clearly. And then half a stroke thickness wide, then a whole stroke thickness, then a half. You can play with that stroke dash array property, get very complicated effects using your dashes and spaces. Dash caps add some thickness to the solid portion. Here, well, I'm not quite specifying any single property. This means my stroke dash array is 2 and my stroke dash cap is round. I get the same behavior for square or triangle. I just chose round for this example. And you can see that this example should look exactly like this one. But it adds on to that this half circle, which adds half the stroke width to either side of my dash. So the space gets truncated a little bit. Here you can see it when I match this example, where I have 2 stroke thicknesses for the solid part and 1 stroke thickness for the space. But if I add the round end cap, and I also add it on the end of the beginning of the line as well, you can see, in this case, we've completely sacrificed the space between each dash in the line, because that round dash cap takes up half the thickness of the line, and there was only 1 line thickness between each one, so half and half adds up to 1 and it's gone. If you want to get around this problem, you can expand the space, which I've done here by using 1.5, and now I have, well, what looks like half of a stroke thickness between each of these little, well, sausages. The stroke dash offset property is a little more complicated, and you need to think about this line in terms of stroke thicknesses. Here I'm copying this demonstration right here, the second one here, and I've set the stroke dash array property to 2 and 1. 2 thicknesses, 1 thickness, 2, 1, 2, 1, and so on. And the stroke dash offset is set to 0, which means I start right at the very beginning rendering that line with its dashes. If I set the stroke dash offset property to 1, imagine a vertical line right here which indicates the starting point, that is at 1 stroke thickness into my pattern. The whole line shifts to the left by 1 stroke thickness, but then repeats exactly as before. If I set the stroke dash offset to 2, now that vertical line is drawn 2 stroke thicknesses in, and my line starts with that first space, and here's where it starts, but again repeats the pattern after that. If I set the stroke dash offset to 3, my line starts 3 stroke thicknesses in, there's 1, 2, 3, and the line starts here. This would all be more interesting if I'd chosen, for example, a line like this one, where the pattern isn't repeating, or it does repeat, but not as obvious as it does here. Anyway, given that stroke dash offset property, you can imagine that I could animate this property over time. By changing the value from 0 to 1 to 2 to 3 and so on, my line would appear to have the dashes moving to the left on the screen. And although we haven't studied animation yet, we will in a separate portion of the course, and you'll learn how to do things like that. Just like the line shape describes a single line connecting 2 points, the polyline shape describes a sequence of connected straight lines. Rather than just 2 points, you've got to provide a set of points. 1 point at the start, then the next intermediate point, then the next intermediate point, and so on until you specify the final point. Each line starts where the previous one ended. Now in code, you could create a point collection, but in markup, you set the points property. You might see markup like this. This isn't very interesting because it only represents a single line, but it could have more. We have polyline, stroke equals black. You must specify the stroke property, and then your points collection. Here we're going from x of 20, y of 12, to x of 400, y of 25. You can also represent the same thing using commas between the x and y coordinates. Some people find that easier to read, so you can see you have ordered pairs for the x and y coordinates. Again, this isn't a very interesting example because it only specifies a single line, but we will look at examples that have multiple lines. That's the point. You must supply at least a pair of points, as we did in the last example. You can use no commas, you can use commas between x and y, or you can put commas between every number if you just like putting commas everywhere. Remember, each line begins where the previous line ended, and if you supply 3 points, you'll see 2 lines. If you want to create a complex series of lines, which could be represented by some programmatic manipulation, you might just find it easier to do the work in code. And if you want a closed polygon, you must supply the final point, which repeats the first one. In that case, you might find it easier to use the polygon shape, which we'll look at next. I will admit to using graph paper to create the demonstrations you see here. In the first one, we have a series of lines which start here and end here, and in the second one, we have a series of lines which, well, as you see, make a star. How do we do those? Well, you can see here, I think the star is actually first and the rectangular one is second, so I'll start with that one. I have a series of points with a stroke of red, stroke thickness is 5, and here is the series of points, 100, 100, 120, 100, 120, 120, and so on. And that created the shape you see here. Each line starts where the previous one ends. So we have a line connecting these 2 points, then a line connecting these 2 points, then a line connecting these 2 points, and so on. For the star, you can see because it is a closed shape, that is, the first point is the same as the last point, I can use the fill property to fill it in. And actually, you can use the fill property even if you don't specify that final line segment. When you specify the fill property, they assume you wanted that final point, and they'll fill it as if you did, though the final line segment wouldn't have been there if I hadn't provided that final point. The geometry for creating a star took me a little effort to figure out. You can see the points are kind of complicated there, but you can do it. It might have been easier to do that one programmatically using some sort of matrix manipulation, but that's a little too advanced for this course right now. At least at this point, you've seen how to use the polyline element by specifying the points collection, and you can use it for an open or a closed shape. The polygon shape is equivalent to the polyline for all intents and purposes, except it automatically closes the final segment for you. There's no need to supply that final point, and really that's the only difference. If you're going to create a polygon, though, you're most likely going to want to fill it. It's obvious how to fill a polygon without crossed lines, but the question is, how do you fill a polygon that has crossed lines? And in that case, you'll need to study the fill rule property. And this can either be set to even odd or non-zero. I will just say that it took me a good long while to figure out the documentation on these two property values, so I'll try to summarize how these work. Here is a complex polygon with crossed lines, and the fill rule has been set to even odd. Setting it to non-zero, the entire shape fills. Why is that? Well, let's go look at the rules. For even odd, here's what the rendering engine has to do. From every point, the rendering engine draws a line to some infinity point outside the shape. Imagine from every point inside, you draw a line to the outside. If that line crosses an even number of lines, the point is considered to be outside the shape and doesn't get filled in. If you cross an odd number of lines, the point is considered inside the shape, and therefore it gets filled. The non-zero fill rule value treats left-right rays separately from right-left rays. Imagine you're drawing that star you just saw. Every ray is either going from left to right or right to left. What it does with vertical rays, I have no idea. But in any case, here, treating left-right rays separately from right-left rays, again, the rendering engine draws a line from every point inside your shape, what you think is inside, to infinity, and it adds 1 for left-right rays and subtracts 1 from right-left rays as it crosses them. If the sum is not 0, the point is inside and gets filled. If the sum is 0, which means it crosses the same number of left, right, and right, left, the point is considered to be outside and doesn't get filled. The answer is that generally fills more sections. You're not going to do this. You're not going to think about even, odd versus non-zero. Try one. If it doesn't do what you like, try the other. Those are your only choices. If you don't get what you want, you have to rethink how you're going to fill this thing to begin with. Let's look at an example that demonstrates the difference between the two. In this demonstration, I've started by creating a simple polygon. I've specified each of these endpoints here for these segments, except I didn't have to specify the last one the same as the first one. I stopped right here. And the polygon shape filled in the last line segment for me. I set the fill property to yellow, and I was done. Down at the bottom, I've used a different way of doing this. I've specified long line segments from here to here to here to here to here and back up. Oops, didn't specify that one because the polygon shape did it for me. So I specified 1, 2, 3, 4 sets of line segments, and the last one got filled in for me. And I copied that markup over to this example. The only difference is when I set the fill property, I set the fill rule property to one of two different values, even, odd, or non-zero. Let's think about it. Why does this point get filled in with yellow color? Well, with the even, odd property, you draw a line from the point to infinity going through the edge of the polygon, and if you cross an even number of lines, you're outside the polygon and you don't get filled. If you cross an odd number of lines, you're inside the polygon and you do get filled. So here, to get to the outside, you just go out, you cross one line, that's odd, you get filled. If you're here and you go out, you cross 1, 2 lines, and since that's even, we're outside the polygon, we don't get filled. You might think, oh, I can bypass this by going through that point. That's just one point right there, one line. Wrong. It's 2 lines. You're crossing this one and this one. Get over it. Over here, oh, and there's no magic bullet. Things don't curve. It's a straight line. Over here, we've specified the non-zero rule. Well, if you imagine how this was drawn, we have a left to right ray, a right to left ray, a left to right ray, a right to left ray, and a left to right ray. So you get the idea here. And if I go from any point here outwards, I cross one ray. That isn't 0, so I get filled in. If I go from here, I'm crossing a left to right ray, then another left to right ray. They don't cancel out. That's non-zero, so I get filled. You're not going to think about this every time you draw a polygon and try to fill it. Instead, try one. If it doesn't work, try the other. If neither one works, and you want the whole thing to be filled in, what you'll have to do is create the polygon out of smaller chunks of shapes instead of using one big polygon. You can always get what you want. It just may take more effort. There's one more wrinkle in the line shape puzzle, and that is using line joins. The stroke line join property changes the way lines join to each other. You can use any value from the pen line join enumeration. There's miter, which uses sharp edges. There's bevel, which cuts off the pointed edge, and round, which gently rounds the corner. You can also set the stroke miter limit property if you're using the miter value, which defines a limit on the ratio of the miter length to half of the stroke width. If you set this to 1, the corner can only extend half the thickness of the line away from the corner itself. Let's look at a demonstration which shows off all of these options. In this example, I've used the same set of lines, a polyline shape, and you can see that where the lines join, there's a sharp edge, actually 2 of them, one here and one here. If we set the stroke line join property to miter, we get this sharp corner on both of those corners. If we set it to bevel, you can see that that corner is truncated. And if we set it to round, we get a nice rounded edge on each of those corners. Finally, if you're using the miter option and you set the stroke miter limit property, we end up cutting off a little bit of that because we've said the limit on the miter, in this case, is half the stroke thickness. It can't extend any farther out than half of the stroke thickness of the line we're drawing. You can see it looks like bevel, but it's not cut off quite as much as the bevel is. So you can experiment with that stroke miter limit if you want to get something more than bevel, but not as sharp as the miter option. Again, these are pretty serious, minute details, but it's nice to know all of the options when you're drawing your own lines.